Hi everybody. So thanks for being here for the last talk of the day. So basically, we're sitting between you and the apero, or we'll try to rush a bit to have a beer as up. I'm Benoit. I'm working as a software engineer at VeriSign. I'm here with my colleague Harry, and we will present you today part of the work we are doing at VeriSign for cluster-to-cluster replication. We'll slice all this into pieces to understand properly what we are doing. So in large Hadoop deployments, usually you have kind of production cluster, and then where all the data lands first, and you have production job running on that cluster. So you want to have a cluster which is fast, but then your job are properly QA'd. You have a tight SLA on the job, and you try to keep the cluster as small as possible just to fit all this data. And then you tend to have a second, bigger cluster, which can be called like research cluster, where you want all the data to land with different lifecycle, like longer retention policy, potentially storing a different folder, etc., where all the researcher will be able to run the job without impacting the performance and the SLAs on the production cluster. So today, at some point, business come to us saying this is a requirement you need to have, so cluster-to-cluster replication, and we start thinking about how we can do that, right? The naive approach on cluster replication is using DCP, for instance. So on the slide, you have on the right-hand side the source cluster. You want to replicate to the replica cluster on the right side. So basically, you have a data replicator, which is polling the main HDFS, either file there, new file, no new file. Okay, you continue polling. And at some point, a file is produced on the source cluster. And then the next time I will poll the source cluster, I'll find this file, and then I kick the transfer. The problem with that, of course, is there's big delay can have potential big delay between the creation of the file on the source cluster and the replication of the file in the old cluster. So on average, the replication time is the polling period divided by 2. So this is the approach we took initially. We used DCP to do that. So once a day, we kick a DCP job. So the delay is half a day. And researcher came and said, OK, we're not happy having this data after 1 day in the cluster ready for our processing. So they were not happy. The second bad issue with that is we started to transfer big chunk of data once a day. So you really see spike in the network bandwidth. So the two data centers are not located on the same physical location. We take, carrier link between two data centers, and at some point the network operator went to our door, ringing to us saying, you can't do that, you're just killing the bandwidth in between, so you need to find something more efficient. A second approach could be the data producer on the source cluster could write into the two clusters directly, but this requires code change, and this is an approach we didn't want to follow. So the second approach we start thinking for having something more real-time is the data replicator should, from whatever mean, register to the HDFS source HDFS cluster, tell me when there's a new file created. And then as soon as there's a file created into the HDFS cluster, then it's notified and the file is created. And if you do things properly, you should be able to do this replication within a few milliseconds. You need to have the time for the transfer, but at least the notification and the detection should be down to a few milliseconds. So we did our homework. We went through Apache Jira tickets. We had a look at what's already existing, what the community is speaking about. We found a few tickets speaking about name node callback or event notification, but all these tickets seems to go nowhere fast. And then we kind of stepped back and said, OK, what's the missing piece in the Hadoop ecosystem to be able to build something like this? And the missing piece is a way to subscribe, to listen to all the events that appear into HDFS, which is kind of similar to the ePOL approach for Linux file system. So then we set ourselves a few goals. So we set the first goal, as we also operate the cluster, We know how it can be a pain in distributed system like this. So we really want to be the event notification system non-intrusive. We don't want to run user code on the same JVM than the name nodes. We want to support both HA and non-HA deployments. We want to keep it with a really low memory footprint and low operation complexities. So we want to be able to kill it and then restart it easily. We want to reduce the number of dependencies, so we want to use the same dependency that the Hadoop code base already has. And then we want to have well-defined interface and API. The goal for that is, while we were working on that component, we find out there's way more use case that can be achieved using this primitive function. We will have our own implementation on the cluster-to-cluster application, but this component is a good candidate for open sourcing. And then say, okay, let's have it modular and let other users build their own complex workflow. And at the end of the day, we wanted to have a bit more fun than only dealing with Hadoop issues like drive failure, and node failure, etc. So from a high-level perspective, this is how it works, how the name node works. So basically, you have your data producer, which is a basic DFS client, which is contacting the name node for a file state change, like creating a new file or deleting a new file, renaming, etc. The name node is then performing the change into his in-memory representation, which is the DFS directory. Then it logs all this into edit log dir on disk. There's some magic happening here that will be covered in detail later. But then it's the name node hack to the DFS client saying, okay, the operation is performed. So we find a cool place, this edit log file, where there's all the transactions that are recorded. So all what's happened into the cluster is recorded. You may remember your old days in dealing with database. It's kind of edit log file, and then there are some nice tools like Golden Gate that is replaying the transaction that happened in the cluster. So that's basically the missing part into the Hadoop ecosystem. So we identified this one, and we came up with a Trumpet module, which is what we will present today. This Trumpet, so in relation of the elephants making noise, which is a trumpeting, because we're basically broadcasting all the events that happens in one DFS cluster. So this Trumpet tool will, from a high-level perspective, it will tail the edit log, and then it will broadcast all the events to the register listener. We tried to keep the initial part really from a high-level perspective, and we took some implementation choice, but you can really plug your own implementation at almost every level. So in a nutshell, what Trumpet is a REST server, which is streaming all the HDFS state modification change. So it's similar to EPOL file system. And it's really cool. It's a primitive function that you can then publish your events in kind of event bus and have a lot of different user or components listening to this event modification. So I'm done with my part, and I'll hand over to Harry, which will talk more in detail how it has been built.
Hello? Yeah, okay. Hi, everybody. I'm Hari. I'm one of the engineers who worked on making the idea which Benoit put forth into code. So I translated everything into code. So I will probably talk about a little more detail about how we went about implementing it. Before I start, how many of you have some experience on looking on Hadoop code, like HDFS code, browsing across? Okay, that's cool. Okay, so on a component level design, like mentioned, we have the FS edit log directory. So the whole FS edit log tailing is handled by the Trumpet orchestrator. So the orchestrator is responsible for initializing the FS edit log finder. So when the orchestrator starts it, it says, okay, this is the last transaction ID I have read. So when you start it for the first time, you can start it with the invalid transaction ID in HDFS, or you can start it with, say you want to start with transaction 5, you can specify that you want to start it with transaction 5, and the finder goes to the fs edit log directory. It scans for what is the relevant fs edit log file which I need to start tailing from, and then it picks up that file. It could be either the in progress file. The in progress file is the active file which is currently updated by the name node, or it could be a finalized edit log file which is already, you want to tail little behind and start and then catch up to the in progress file. So you can do either of that. So once you have it, we call something which we construct which is called the orchestra. Orchestra is nothing but reading all the operations which is recorded in the edit log and then playing as events across to whoever is interested in playing it. So this orchestra keeps on repeating. It's kind of a continuous process. So every time, whenever edit log finder returns back a fs edit log file to be tailed, it calls the tailor tails it. So since the edit log is going to be a binary stream, what we do is we have a buffer in between, which is like a blocking queue. So you keep on pushing whatever stream you get from the edit log into the queue, and then we have an edit log decoder. Basically, decoder constantly listens whether there is any new stream being added into the queue, and then it consumes it and then tries to decode it to a valid edit log op, and then it sees, okay, if there is any listener for it, and then it publishes to it. So, right. So if you look at the whole component design, right, it's like just tailing a binary stream. So what's so complex about tailing a binary stream? So that's what, when we started about it, okay, it's a simple Unix-based tailing. We just tail a file and get all the streams, push it into a queue, and then read it. But when we started implementing it, it became far more complicated than we imagined, right? So this is because of the unique way the name node kind of initializes the fs edit log. So whenever the name node initializes a new edit log in progress file, it initializes with -1, which stands for all the invalid opcode. So it initializes a 1 MB chunk and then puts in invalid opcode all across. So I don't know what's the technical reason behind it, but we try to use all the Hadoop-based fs edit log parsers and readers. So the way the fs edit log op reader reads, when it tries to read the operation, it tries to find an invalid opcode. So if it finds an invalid opcode, it thinks that it's the end of the fs edit log file. So it kind of sees that there should not be any more operation recorded in the fs edit log. But when you try to tail all the binary stream, you just encounter invalid opcode and you pass it to the decoder. The decoder finds, okay, it tries to find there are any more operations and it finds invalid opcode. It starts throwing weird exceptions. So what we started doing is we implemented a smart tailer which kind of knows, okay, if I encounter an invalid opcode, it doesn't mean that it is end of the file. We try to find whether there are any more stream left, and if it has consecutive invalid opcodes registered in the fs edit log, we know that this is an in progress file. There might be more operations might be recorded by the name node gradually. So we kind of hold a pointer in the binary stream till which point we have read. And then we go for, the tailor sleeps for a while and then comes back and sees whether there's new stream coming in. So if you look at this, so the name node starts recording the operations into the in progress file, and then the tailor comes in. So the tailor finds, okay, I want to start tailing in progress file, and then it figures out there are operations recorded, okay. It reads the operations, and then it finds out the invalid opcode, and then it finds there are a lot of consecutive invalid opcodes further, so it stops, and then it sleeps, and then meanwhile the name node records further transaction. So the tailor wakes up and then it figures out, okay, there are more operations, I will start reading it. So what might happen is when the tailor is reading all the operations, the name node might finalize the edit log file segment. So what finalize means is the in progress file gets rolled over and then it gets finalized. So basically it says, okay, it is not any more in progress file. So this is an edit log which contains all the operations from transaction ID 1 to transaction ID 1235. And then it ends with the -1 at the end. And then it starts creating one more in progress file and starts recording the transaction later. So what we do is the tailor finds out, okay, the edit log file has been rolled, and then it says the orchestrator, okay, the file has been rolled, and then the tailor and says, okay, this is the last transaction ID I have read. And then the orchestrator calls the finder saying, okay, this is the transaction ID which has been read recently. So can you find the proper edit log file? So the finder is smart enough to go and figure out, okay, it seems that the edit log is not fully read, so I need to still read So it goes back, and then it starts tailing from there. And then it picks up, okay, I have already streamed operations till 8, and then I need to stream rest of the operation, and it streams it, and then it figures out, okay, I have reached end of the file. So it says, okay, I've read fully, and then the tailer goes to the in-progress file and then starts catching up. So everything happens in delay of a few milliseconds. So we try to make sure that we don't miss any operations when you're tailing an active edit log file. So this is the whole high-level architecture. So this doesn't cover the piece where we start publishing the events. So it has two components. The major principle we kind of adapted here is we try to follow the open-close principles, where it's close for modification and open for extension. So what we did is, this is a piece which could be used by anybody. So we built in a very minimalistic design where we get the edit log which is being decoded, and then we convert those events into an Avro schema, Avro file, and then we start publishing it. So we have a Netty-based event server which kind of listens for whoever is interested for events, subscribe to me, and then when somebody subscribes to it, it holds all the topic listeners for a corresponding event. So the publisher looks up the event listener, topic listener, sees whether there are any listeners registered, and then it starts streaming the events via the Netty channels. So this is like a minimalistic implementation which we have done. The reason which we did is we wanted to have a POC, and then we want to make it extensible and flexible so that people can have their own implementation. Like you want to have a different topic listener, or you want to just decode all the operations and then stream it into Kafka or any kind of message broker. So you want to have flexibility in those kinds. So it's all defined by well-defined interfaces. So you can implement your own publisher, and then or you can stream it whatever you want to do. So the default implementation which we came up for our needs, and we are planning to open source it, it comes up with the following endpoints. Say if you want to listen to all the events in HDFS, you just say get /, which means that I want to listen to whatever is happening in HDFS. Or you can say I want to listen to a particular directory. Or you can say, okay, I want to listen for a success file. This is a typical case which you implemented where data is being processed. At the end of the data processing, you just drop a .success file, and so the Trumpet listens for it, and when it finds a success file, it starts copying the data between the clusters. This is a simple replication scenario. Or we classify events into different umbrellas. So we have three class of events. One is add, or rename, or delete. The name is so self-descriptive. And then you can also listen on a particular file pattern. Say you want to listen for any LZO file-based operation happening in the cluster, you can just listen for it. Or you can have a combination of everything. I want to listen to a particular directory and look for add operation, and then look for a file pattern matching LZO. So this is the events Avro schema, which when the edit log decoder decodes it, it transforms into this Avro file. So it has the transaction ID, and then it has the type, which is what I said. It could be either add, delete, or rename. And then this has the path. So which path, what is the file path which has been created in the cluster? And then if it is a rename operation, it also passes the source path. So it is an optional one, as you can see. So it depends upon what kind of operation is being read across. So the whole event filtering and classification. So within HDFS, there are a lot of low-level file system operations which are happening. So what we have done is we have cherry-picked few of the operations which we think might be relevant for the users. So right now, what we've done is we have marked, these are all the low-level file system opcodes. So op add, op make the error, say HDFS file system op. So we mapped it to add, and then op rename and op rename old, we mapped it to rename, and delete and concat delete, we have mapped it to delete. So, so this is the high-level implementation. This is the implementation which we've done. So now I want to go back and say, aligned to what Benoit was kind of pitching in. We had some design goals. We try to see how we kind of fit into the design goals. So we wanted to make it flexible. So we have the configurations for the registry. So the registry is the part where you can say whether you want to have an in-memory registry or you want to have a message broker where you can register for events, and then you can push all the events into there and consume it from there. So you can also configure it via there. And then for the tailor, you need to specify where your edit logs directory is being configured in the cluster. So when you specify, Trumpet will start tailing for edit logs from there. And this is the sleep interval. So if there are not any more binary stream which is absorbed by tailor, it sleeps for this 100 milliseconds and then comes back. And the last stream transaction ID, this is what I was saying. So say if the Trumpet crashes, or if you want to do maintenance over Trumpet, you know what transactions still you have streamed. So when you restart it, you can specify, okay, this is by default, it's the invalid transaction ID. You can specify, say I want to start from the transaction N, and then the Trumpet will start finding out the corresponding edit log file and then start streaming transactions from there. And then these are all the default implementation we have. This is for the Netty REST server, so at what port it runs and the number of worker threads which it needs to process the event listeners. And the final thing is, okay, what is the memory footprint going to be? So we use a blocking queue, which is going to be the main memory resource consumer here. So we have parameters where you can size how much memory you want to allocate to it. So by default, we have we expose two configs. We use a blocking queue, so the blocking queue has n number of slots. So you can say what is the maximum number of slots you want to provide to the queue, and then you can say within the queue what is the maximum message size which you want to push it into it. So the cross product of these two is kind of a fair reflective number of how much memory Trumpet is going to consume when there is a lot of events happening in the cluster. So far I talked about all the server-side streaming part. So at the client side, we want to provide some simple libraries. Since we are completely based on an asynchronous way of generating and consuming events, we are providing asynchronous library so that you need not worry about how you need to set up a async client and start streaming the event. So you just need to implement this interface. So this interface has just two methods on event. So if there is an event happening in the cluster, how I want to handle it, and then if there is any area, how you want to handle it. So once you implement the interface, you can launch a client saying, okay, it comes up with a simple launcher script. You can specify, okay, I want to listen to the particular endpoint, and then I want to say this is the handler for this endpoint. So what the listener does is it spins a daemon, and then it starts subscribing to the server, connects to the server, and then when there is any event, it delegates it to the event handler. So it also reduces the boilerplate code where you want to stream the response and then convert it back to an Avro schema, which I talked about, and then it just gives you you can just implement a simple POJO for your handling part. Okay, so all the talk we have been mentioning about the real-time replication use case. So that was the main driver. So when we started looking at it, okay, we wanted to do a real-time replication, but we identified, okay, it needs a primitive where we want to record all the events happening in the cluster. So Trumpet is not only kind of useful only for real-time replication use case. There could be more possible use cases which you can use. One of the typical use cases is job chaining. Say you have two teams. One team might be dependent on processing of the other team. So usually there are some kind of coordination, or they start their job say after 1 hour of the previous team's job completion. And most of the time, if there is any issue with this workflow pipeline breaks. So you can use just Trumpet for it. So you can listen for the corresponding job completion. So you can listen for the file, which is kind of indicator of when the job is complete, and then you can chain it accordingly. You can also use it for monitoring. Say you want to look at, okay, I have a feed which needs to flow in a particular rate. You can just subscribe for the corresponding path in HDFS and then listen whether the files are flowing constantly into the cluster. The other kind of use cases which you can build on top of it is you can listen for all the events happening in the cluster, and then you can archive it into any kind of message broker. And then if you say at any point you want to replay it and see what was the state change which happened in the cluster for any kind of debugging purposes, you can do it. So it's basically a primitive which you can use for building all the sophisticated workflows. So right now we have the POC ready. We are in the last stages of open sourcing it. Should be available anytime soon. Going with the true Trumpet spirit. I would recommend you to listen to this HDFS Trumpet tag, Twitter tag, and then you will get to know, listen to all the events happening. So you will get to know when there is any open sourcing activity going on there. And these are all our Twitter handles if you are interested to know, explore more about Trumpet. Yeah, thank you. Any questions? Yeah.
On? Hello? Oh, great. Yeah, so in an HA environment where the different nodes are becoming active at different times, not one single node has a complete picture of all the edit log segments in the edit log. And the in-progress edit log also changes between these two different nodes. Do you guys handle this in Trumpet?
Did you get the question? I didn't follow it.
HA. So the question is, do we handle HA, right?
Basically, yeah.
Yeah. So so far we can plug either in the name node or listen to the edits from the journal nodes, and supporting the HA, which means on our side storing what was the last transaction ID that is processed, and then replaying from another node if this one goes down. This is a part which is in our roadmap. So we're not there yet.
Okay. So I guess like one more question then. Would it be, if you were to not make this a separate system but actually integrate this into HDFS, wouldn't this be a little bit easier? Because you could just add sort of another journal node, which is like a watcher-only journal node, which doesn't vote in the quorum, and we just get all of these edits being streamed to it in real time. You wouldn't have to worry about like this time of the tailor and all that stuff. But you consider that kind of architecture as well?
Yeah, so we had this idea at some point, and we thought about supporting non-HA deployment too, which then makes this case obsolete, right? But I mean, one of the ideas then to act like this, and to support only HA. Or if we support HA, we support through journal node listed.
Yeah. So one of the thing which we looked up before implementing the tailor is the standby node mode. So the standby node mode also does this tailing. So it has a tailing frequency. Some of the aspects which we considered is we want to be as close to real time as possible. And the standby node only starts tailing the edit logs which are finalized. It doesn't start tailing the edit log which is in progress. So it depends upon what kind of activity is happening in the cluster. So you might have the 2 minutes lag in between. So we wanted to have a feature which is as close to real time as possible. So that's also one of the reasons why we started implementing our own tailor.
So one final question though. Since you are an external service, you have to deal with edit log format changes. Are there any issues with that with like many versions of Hadoop?
If there is any edit log format changes, we need to make it compatible to it. So that's one of the things. So the plan is, if this seems relevant, we might want to contribute to the community. If it goes in, then the edit log changes would also be compatible automatically. If not, then we need to make it compatible if there is any changes, especially all the file naming convention and all the way the edit logs are recorded. If there is a change, we need to take care.
We've actually considered adding sort of consumer APIs for services like yourself, right, which don't want to be parsing edit logs manually, they can avoid it. So we should talk afterwards. Thanks.
Thanks. Yeah, I agree with Andrew that it would be great to have this in HDFS rather than external for all those reasons because, format changes can be a big problem. There's already enough moving parts. One thing I'm curious about, sorry if you already explained this, but what happens if the TCP connection drops? So it seems like you're making this call with, like, let's say a GET, and then I receive a bunch of stuff in the TCP connection. Basically, it's sent in JSON, right? Or
it's
is it
Avro? Yeah.
Avro, okay.
Yeah.
It's sent in Avro. But what if the TCP connection drops? Do I have a way to get back to where I was, or how does that work?
You mean at the client side or on the server side?
Well, the connection between the client and the server.
Okay, so from the server side, the server, before publishing any events, it looks at whether the connection is still valid. If the connection is not valid, it kind of re-registers the client. From the client side, if it dies, it can restart. So when it restarts, it misses all the events. Right now with the current implementation, it misses all the events which has happened in the meantime. So that's where we want to add a support where you can say from the client side, I want to start streaming from this transaction ID, which would be a much nicer feature, so that the client can recover from the state it was able to consume events.
Right, and that's another feature that needs integration with HDFS, because we do purge edit logs eventually.
Yeah, so the default configuration which we looked at, it depends upon what activity we have in the cluster. The number of finalized edit log segment which is retained is, if I'm right, it's 1 million transactions or something. So it depends upon how many edit logs it generates for 1 million transactions in the cluster. If you have a very busy cluster, probably it might be few files. If it is, if you have very less activity, you might have more edit logs in the cluster.
Okay, thanks.
Question in the back.
Hi. So one question about edit logs. Would it be possible to use audit log from HDFS? So stop reading the edit logs, but there's like this audit log, right, with the information of like creation or edit of the file. Would that be possible to use?
What is it? Sorry, I couldn't hear you properly.
So there's this audit log file, right?
Oh, okay.
And it's a text file, like tab-separated text file, where you can see like different operation in HDFS.
Okay. I'm not sure. I think Adam covered it. So I think, if I'm right, audit log is kind of audit of all the files being accessed by the users, right?
So audit log logs all requests into the main node, even read-only requests.
Yeah.
Open a file. Edit log has only modification.
Yeah. So we are kind of scanning for the actual state change which is happening in the cluster. We are not interested on who is trying to access what.
Okay.
Okay.
And also a second question: do you support a situation when a journal node goes out of sync? Yeah, but it's like there's a quorum, right? So it's like basically possible that one journal node will go out of sync, right? And that's possible, right?
Basically, journal nodes can't diverge from each other, or at least the committed transaction IDs on the journal nodes can't diverge from each other. And it is important to make the distinction between the committed transaction ID and the latest one there. But if you make that distinction correctly, then there's no divergent history possible.
Yeah.
And actually, this is an issue with HA too, because the log is a right behind log, right? So if you let's say that my name node gets a request, writes it to the edit log, and then it dies before it returned that to the client. Then there's a failover. Well, I guess there's some tricky scenarios in there, and that's why I'm not really comfortable with this approach of just going through in progress and.
Yeah, currently the limitation is the Taylor should run in the node which is active in the cluster. So if the active component dies, it is not smart enough to switch back to the cluster, to the component which is active. So that part is not done. This is like a very minimal version. It's kind of a POC version which we have right now.
Yeah, I can think of a few scenarios that might be problematic there, and I think that's something to think about, certainly.
Sure.
Some of those you could solve, but some of them, like I said, I think this needs more integration with HDFS. That's my thought.
Okay.
Any other question? If no, thank you very much, guys.
Thank you.